I'm Dave Brown. In this training program, we're going to cover two kinds of belts. Now, we're not going to cover the belt in the mouth, and we're not going to cover the belt of scotch and water. We're going to cover timing belts and flat belts. And timing belts will be our primary concern, but we will devote a few minutes to flat belting later in the program.
Now, what is a timing belt? Well, basically, it's a flat rubber belt molded with teeth on one side. It gets its strength from a tension member, and as you can see, it has teeth down the inside and is a continuous belt. The timing belt may be smaller or larger than the one I'm showing you. It is similar to roller chain in that it is a positive drive. It is also similar to silent chain and operates on very much the same basic principle. When we use the term positive drive, we mean there's no slippage at all, and since every tooth must mesh, the timing belt is a positive drive. Now, first of all, we need to look at just what goes into making up a timing belt, which I've cut in two so we can see the various components. First, we have the tension member. Now, this is the muscle in the belt, and it differs from a regular flat power transmission belt, which gets its strength from thickness. As you can see here, the thicker this belt is, the stronger it is. Let's take a moment to discuss how timing belts are made and how this affects the tension member. Timing belts are made on a drum. A single belt, 14 inches wide, will be made on the drum, and the individual belt, such as the one you see here, will be cut from that belt a slice at a time, cut from the larger belt during fabrication. Now, to get the tension member into the belt, it's started and is wound around the drum like a fishing line might feed onto a reel. Because it is continuously going around, the tension member actually forms a helix angle. In other words, it is at a slight angle to the cut. By looking at the threads on this pipe, it may help you to understand the term helix angle, which we will be referring to again during the tape. Now, when the individual belt is cut off the original wide molding, it's cut without reference to this member. And, as you can see, we've sliced down the middle of the tension member from here to here. And as we cut off a slice, we find that this helix angle causes a problem, which we must take into consideration, and we'll discuss that point in just a moment. The teeth on the belt are usually neoprene, and the root of the tooth here is essentially the pitch line, though in actuality, the pitch line is the center of the tension member instead of the root of the tooth. The broken line on this picture shows the tension member, which is the true pitch line. I might interject a point here. As long as 6 or more teeth are in contact with the sprocket, the teeth are strong enough so that they will pull the tension member apart rather than stripping the teeth from the belt. The belt backing is the section of rubber above the tension member. It is normally neoprene and is cast integrally with the tension member and with the teeth as shown here. Now, again, these are normally neoprene, but they are available in a number of other materials for specific applications. One special application, for instance, might require special static conducting materials. While neoprene is oil resistant, if the unit is to run in a bath of oil, some different material, such as Buna-N, may be required. Buna-N, although it looks like neoprene, is an entirely different kind of rubber. The standard belt will normally operate in the range of minus 35 degrees to plus 185 degrees Fahrenheit. Now, if you want to go above or below this range, we can, with special materials, go as low as minus 65 degrees Fahrenheit or up as high as 250 degrees Fahrenheit. Now, the units that I've just mentioned are all special orders. They would require a relatively long delivery. The last component we come to is the belt facing, which is the cover on the inner face of the belt. This material is normally a nylon fabric, and under normal service, it polishes to the point of having a slick, shiny appearance. And although this facing is the only part which is subject to much friction, it will normally outlast the other components of the belt. There are a number of reasons to use or not to use a timing belt. First, let's compare it with a friction or non-positive drive, such as a V-belt. Now, the timing belt obviously has an advantage if you're trying to maintain a constant relation between two pulleys, because with the teeth along here, we don't have any slippage at all. As a consequence, we do get a positive drive. As compared to a normal V-belt drive, the timing belt requires less tension. Since on the V-belt drive, you must pull the belt relatively tight in order to minimize the slippage. But with a timing belt, this is not necessary. And since there's less tension, you'll reduce your bearing loads and have longer bearing life on the motor or other drive components. There's higher mechanical efficiency with the timing belt drive. On a V-belt drive, you normally lose about 1% speed in terms of slippage, or creep as it's sometimes called, and this is not true with a timing belt drive. Again, the reason for this, the timing belt is a positive drive. The timing belt pulleys, or as we will call them, timing belt sprockets, are usually smaller than V-belt pulleys. Usually, we can run a timing belt drive at higher speeds because the belt itself has less mass for a given capacity. And these last 2 points means you get a more compact drive, which in today's space-conscious world usually is a factor. But now, we know nothing is a cure-all, and there are some disadvantages to a timing belt when compared to a V-belt. First of all, many belts must absorb shock loading, and since the timing belts do not slip, they don't absorb shock loading nearly as well as a flat belt or a V-belt might. Also, it's relatively noisy at high speeds. Finally now, and probably the most important consideration, it is relatively higher in initial cost. Now, some advantages of timing belt drives as compared to a roller chain or a silent chain drive, which, by the way, are both positive drives. First, and one of the biggest points, there's no lubrication required. There are a great number of places, such as in a textile mill, where we can't cover the drive mechanism effectively with an oil-tight belt case, and as a consequence, anything that must be oiled gets oil on the product. And it goes without saying, if you're getting oil on the product, this is not good. So the fact that it requires no lubrication is a big point in many applications. Secondly, as compared to chain, it is very lightweight. Third, there's no belt stretch. Therefore, once the unit's installed, it doesn't require any further adjustment. As compared to silent chain or roller chain, it doesn't have any moving joints. As you can see, there are no joints, and as a consequence, there are no points of joint wear. Also, we're not exactly restricted to a particular center distance, as we are with gearing, since an idler pulley may be installed for odd center distance. One final advantage, the timing belt will operate at higher speeds than normal roller chain. Now, as compared to roller chain and silent chain, what are some of the disadvantages of timing belts? Timing belts are most suitable for moderate and high speeds, but if you're going to low speeds with high torques, roller chain will have a distinct advantage. As compared to chain, it has a lower maximum load carrying capacity. Although it is not as restricted to center distance as gearing might be, it is more restricted to center distance than chain because we cannot, as we do in chain, take out a link and reduce by just one pitch. We are basically limited to standard sizes. However, special sizes can be made to order. For example, an odd number of teeth on the belt, or special sprockets, which are not normally stocked, are available on special order if there's enough volume involved. Naturally, specials always involve longer deliveries. There are a number of different sizes of timing belts. If you'll notice on this chart, there are 5 normally stocked pitches of timing belts, and these vary according to pitch and width. Let's take a look at these sizes individually, and we'll review the chart in a moment. The smallest is known as XL, which stands for extra light, and it has 1/5 of an inch pitch. The center of this tooth is 1/5 of an inch from the center of the next tooth on this little timing belt. The next size is the L, or light belt, and it has 3/8 of an inch pitch. As you can see, from here to here is 3/8 of an inch. The H, or heavy belt, follows, and it has a pitch of 1/2 inch. Again, 1/2 inch from center to center. The XH and XXH belts are the next largest sizes of normally stocked pitches in timing belts. The extra heavy belt has 7/8" pitch, and the extra heavy belt has 1 1/4 inches pitch. Now let's go over to the chart once more and make sure we understand the letter and pitch designations for the 5 normally stocked pitches of timing belts. 1/5 inch pitch, XL or extra light. 3/8 inch pitch, L or light. 1/2 inch pitch, H or heavy. 7/8 inch pitch, XH or extra heavy. And 1 1/4 inches pitch, XXH for extra heavy. All the belts you have seen are available in varying widths. This belt, a 1000 H300, is an example of the contrast in widths and lengths, although the pitch is the same as this belt, which is a 240 H100. Now, since we've discussed sizes of timing belts, I think now would be a good time to discuss nomenclature. This is a number 240 H100 timing belt, and the nomenclature breakdown goes like this. First, the 240. That means the pitch length of this belt is 24 inches, or another way of saying it, the distance around the pitch line of the belt is 24.0 inches. The H identifies it as 1/2 inch pitch, and if you'll remember from our discussion, this 1/2 inch pitch is measured from here to here. The 100 stands for 1.00 inches. This means the belt is 1 inch wide. This belt is an 80 XL 037. The 80 means we have 8 inches pitch length, or the distance around the pitch line. The XL stands for extra light, or if you remember from the chart, 1/5 of an inch pitch. The 037 means 3/8 of an inch, or 0.37 inches wide. With timing belts, we obviously need sprockets. Like the belts, the sprockets are made in varying widths as required. Therefore, we do have various width and pitch sprockets, and I'll show you 2 or 3 of the standards. Here is a minimum plain bore sprocket, 1 inch wide, 1/2 inch pitch. And as you can see, the belt runs right on it. Now, I'll tell you about the nomenclature of sprockets in a moment. We can also use a taper lock hub. Everything with the taper lock hub will be basically the same, except the taper hub goes in here. By the way, these are also available with QD hubs. An explanation of the QD and taper lock hubs is available in our roller chain tape. If you'll notice, the sprockets have flanges on the side to guide the belt. The reason this is necessary is because of the little helix angle I mentioned before. The belt tends to run sideways, so we have guides on each side of the sprocket. Normally, the guide is on the smaller sprocket, and as you can see, the larger sprocket would not normally have guides. There will be cases, however, where it will be necessary to have guides on both sprockets. For example, a vertical drive should have guides on both sprockets. This particular one uses a QD hub as compared to this one, which uses the taper lock hub. The nomenclature for sprockets is somewhat similar to that used with the timing belts. The sprocket we have here is a number 14 H100. Again, as we did with the belts, let's break this number down to identify the sprocket size. The 14 means the sprocket has 14 teeth. The H stands for 1/2 inch pitch, as it did in the belts. The 100 indicates the width. Here it would be 1 inch wide. By now I'm sure you see how similar the sprocket nomenclature is to the belts. The only difference is in that first number. For belts, the first number indicates pitch length. For sprockets, the first number indicates the number of teeth. Let's take a look at another example. Here we have a number 32H150 sprocket. The 32 indicates the number of teeth. The H indicates 1/2 inch pitch, the distance from here to here. And the number 150 tells us the sprocket is 1½ inches wide. One thing we discussed a moment ago is installation. When we install the belt and sprocket, we don't require that the belt be as tight as the V-belt would be. A snug fit will do, since the teeth actually transmit the power. The chief exception to this would be in real heavy shock loading or reversing type service, where it may be necessary to make them relatively tight. If on heavy shock loads the belts aren't tight enough, we may get what's known as ratcheting or slipping of one or more teeth, and obviously this will wear out the belt in short order. Too few teeth on the power input or drive sprocket is one of the greatest points of failure on a timing belt. In your catalog, you will find a recommended minimum number of teeth for the sprocket. Whenever possible, you should add 4 teeth to this recommended minimum. If the minimum is 16, a 20 will make a much better drive, unless, of course, you require the speed reduction, or for some other reason you must use the smaller sprocket. Misalignment is also a cause of failure, and care should be exercised when we install to make sure that we do align the 2 sprockets as carefully as possible. In service, frequently this sprocket, as we see, will be the drive sprocket, and the larger driven member will be a flat-face pulley. In this case, we normally try to stay at least 6 inches or larger for the flat-face pulley, because only friction does the driving, and the more friction surface on the flat-face pulley, the better. Also, we must pull it tighter than normal so that there will be sufficient drive friction when using the flat-face pulley. In some cases, it is not possible to move our centers, and since we are limited, as we mentioned, to what is available in standard belts and sprockets, we must use a larger belt than necessary and put an idler on the unit to take up the slack. In this case, the idler would be put at some point as indicated here, if it is going to be less than 6 inches in diameter, and it should have teeth. If it is 6 inches or more in diameter, it may be put directly in here. And in this case, we would use a flat-face pulley rather than one with teeth. In summary, we should make a few other points pertaining to timing belts. First, you should never pry the belt over the sprocket flange. You should move one of the units so that the belt may be slipped over the flange. If it has an idler, the idler may be moved instead. If the belt is pried over the flange, the tension member is sure to be damaged, and this will cut belt life to only a fraction of what it would have been otherwise. Another point, it is also possible to use the idler on the back side of the belt. However, this is not a preferred practice, since it makes the belt flex in 2 directions, which tends to reduce belt life. How about storage? Timing belts should be stored in a cool, dry place and where they won't get any sharp bending or creasing. The small timing belts are frequently creased or pressed completely together, and this sharp bending leaves the possibility of completely breaking the tension member. Although timing belts are not a cure-all, they do have a distinct place in industry. Now we take up a type belting completely different from the timing belts we've just been discussing. This is flat belting. Flat belting is one of the oldest methods of transmitting power in use today. About the turn of the century, flat belting was almost exclusively used in any power transmission application that had any appreciable speed. It's still widely used today, although recently its use has been less and less in most operations. Now, this is not because it doesn't do a good job, but because other methods of belting take up less space and are a little more convenient for replacement. As a consequence, the standard flat belting is not as widely used as it once was. Some of the newer, thin, high-capacity flat belts are gaining, but we'll discuss these in a moment. Probably the first material that was used for flat belting was leather, and it's still in wide use today. There are a number of other materials, however, that have since started coming to the front. For many years, cotton woven belting was used. Then, at a later date, this was impregnated with rubber, bonded and vulcanized all in one piece to make a rubber belt. In more recent years, all types of nylons, polyesters, dacron, and other synthetic fibers have been used. At one time, even camel hair was an item used for belting. The one we're showing, by the way, is rayon. Now, since the most common belting is leather, let's discuss it a bit. First, it is available in 3 different weights and 3 different plies or thicknesses. Light, medium, and heavy are the weights. Single, double, and triple are the plies. Now, this nomenclature is used together so that you may have, for example, a medium weight double ply belt. Now, since a cow is only 5 or 6 feet long and a belt may need to be many feet long, we have a problem. But to get around this problem, strips of belting are normally cut into 46-inch lengths, which are then spliced together. The ends are skived or cut off on a slant, and they are normally cemented together with waterproof glue. If the belt is to be more than 1 ply, then the plies are cemented together. The hair side, or the smoothest side, normally runs next to the pulley, while the flesh side, or the strength side, is on the outside. Most leather for belting is cured, or tanned as it's called, by soaking it in solutions of various tree barks. This gives a strong, pliable leather which serves adequately in most applications. Leather was the standard in the industry for many years, and even today, efficiency of belting is given in comparison to leather. There's a different method of tanning, however, which produces a belt with a better coefficient of friction. Coefficient of friction is defined as a measure of the friction or slip when one surface slides on another. This second process uses a tanning solution with mineral salts. These are known as chrome-tanned leather. These differ from the term oak-tanned, which is applied to the process using organic materials. Chrome leather is easily identified by its light gray color. The chrome-tanned leather is normally more pliable, it is water-resistant, and as mentioned, has a higher coefficient of friction. It isn't, however, as strong as oak-tanned leather. Frequently in multi-ply belts, the 2 different leathers are cemented together to get the advantages of both. In some belts, which need especially high strength, a sandwich has been made using fiber or leather for the top cover, a center of nylon or polyester for strength, and a chrome leather cover for the contact side. Now, this gives about the optimum in strength and resistance to slip, since the chrome leather has a very high coefficient of friction. The polyester or nylon is among the strongest materials available. Next most common in terms of usage after leather is flat rubber belt. This is normally constructed of a fabric duck reinforcer, which is coated with rubber by running it through a set of rolls called a calender, which rolls the rubber into the fabric. This coated fabric is then combined with alternate layers of rubber sheets. The whole thing is then vulcanized into one solid mass. If the edges are wrapped around with the canvas, the belt is called folded edge. If the edges are left ragged and trimmed to make them square, the belt is identified as raw edge. The canvas duck is the tension member, and in some types may be stitched, although the bonding of the rubber is normally sufficient to hold it in place. The belt is normally identified by the weight of the canvas duck and the number of plies. For example, 4-ply, 32-ounce belting. Woven belt is in fairly common usage, and here the whole fabric is woven into one solid mass. It may be composed of cotton or synthetics and may be coated or uncoated. It usually has stripes running down its length. These indicate how many plies are in the belt, 1 stripe for each ply. This belt is 5-ply. The connecting together of the ends of both leather belts and cotton belts is done by any number of ways, either lacing the ends together or with steel clips or wire hooks which interlace between the belts like this. As you can see, these are a series of wires. They must be installed with a special machine. Now, when this type is used, they can be installed by simply using a hammer to pound the connector into place. Once there's a connector on both ends of the belt, they are interlaced. and this special two-piece connecting wire is installed. This then is used to join the ends of the belt. Another way, the leather belting could be spliced together by skiving or cutting the ends on a slant and then cementing them in place. This makes for a strong splice, but it takes a good bit longer, so in most cases the ends are joined by mechanical connectors of one type or another. One of the most important items to remember when making a joint of any type is to explicitly follow the instruction of the manufacturer of the connector. With the advent of synthetic fibers, flat belting became more versatile. Synthetic materials first were interwoven with the cotton to give added strength. Later, belts were made entirely out of synthetic fibers such as nylon or dacron, although most of them use some type of rubber cover. In recent years, there's been a new innovation to the flat belting field. This has come about since, along with the high-strength materials which had previously been developed, research has come up with new high coefficients of friction materials. As a consequence, there are now on the market various belts which are, as compared to the old leather belts, 1/4 as thick and possibly as little as 1/4 the width, transmitting the same amount of power. These belts are able to operate on very small pulleys since they are thin in cross-section, which makes them possible relatively high ratios of speed reductions. Because they are so thin, they can't be joined with the normal belt clips or belt lacing that's used with the standard belting. These must be bonded into endless belts, and there are various methods of doing this. Most manufacturers have their own method, and it usually requires special equipment. These new materials are making possible flat belt drives, which are competitive in terms of price and size with many V-belt drives. And there is a possibility there will be a comeback in this field for the flat belting with the new styles of high strength, low weight, and small size flat belting. As in the case of all other belts and chains, pulleys are required for the belts to operate on. Today there are 4 basic materials used: steel, cast iron, paper, and wood. These are all furnished either solid or split hub, and with taper bore hubs or with bored to size hubs. I've just covered the most common types of belting. There are many other specialized products which have been used through the years, and many are still in service. These are for things like extra high temperatures or extremely wet conditions or corrosive atmospheres of one type or another. If you have a special requirement, someone probably already makes the belt for it. This concludes today's tape.